everyone, this is Babitha, working as Assistant Professor in the Department of EC at Institute of Aeronautical Engineering. In this session, I'm going to discuss about phase shift oscillators, in that RC phase shift oscillator as well as Wein bridge oscillator. So while coming to the contents, just I'll revise what is meant by oscillator and what is the basic working principle required in order to operate the oscillator, and RC phase shift oscillator and Wein bridge oscillator. So while coming to the oscillator here, why we are moving for the oscillator even though we are having the amplifier here means the function of the amplifier is to amplify the applied input signal. So at the output of the amplifier, we can expect the amplified version of the applied input signal. Okay, so for the amplifier or from the amplifier, we are getting the amplified version of the output, but along with that, we are getting some distortion or noise also. So in order to remove that distortion and noise, we are introducing the feedback to the amplifier. So how we are introducing the feedback to the amplifier here? We are taking some part or some sample of the output signal from the output of the amplifier, and we are giving back again to the input of the amplifier through the feedback network. Okay, so this feedback, in what way we are giving, whether we are giving the positive feedback or negative feedback, depends upon the applied feedback signal. We can able to estimate whether it is the positive feedback or negative feedback. Suppose if we apply the negative feedback to the amplifier means, so generally our amplifier is having like this. For this we are applying the input signal and we'll get the output signal. Okay, when we are adding the feedback through the feedback network, so we will get the feedback signal here. So the input for the feedback network will be not only. So here, this feedback signal, either we will add or subtract with the, input signal here, so that we will get here it as Vs. So this particular signal we will take it as Vi. Suppose if we use the positive feedback, the value of this Vi is equal to Vs plus Vf for positive feedback. And suppose we are applying the negative feedback, in that case our input signal is difference of source voltage and the feedback voltage in the case of negative feedback. So about negative feedback we already discussed. When we provide the negative feedback to the amplifier circuit, so that it becomes the feedback amplifier. So in the case of amplifiers, we are having 4 types: current amplifier, voltage amplifier, trans resistance amplifier, as well as transconductance amplifier. So for these 4 amplifiers, when we provide the negative feedback, we can able to get different 4 types of feedback amplifiers. Those are voltage series feedback amplifiers, okay, and voltage shunt feedback amplifier, and current series feedback amplifier, and current shunt feedback amplifier. So when we add negative feedback to the amplifier circuit, we will get the 4 different types of feedback amplifiers. And we have seen the analysis of all these 4 negative feedback amplifiers. Okay, and in the case of positive feedback as well as in the negative feedback, why we are preferring both here? In the case of negative feedback, it is providing so many advantages. I have already mentioned, from the output of the amplifier, along with the amplified signal, we are getting the noise as well as distortion also. So when we add the negative feedback to the amplifier circuit, we can able to reduce the noise as well as distortion levels of the output signal, and also we can improve the bandwidth of that particular amplifier. So that's why we are going for the negative feedback amplifier. But the basic disadvantage of negative feedback amplifier is the gain value will be decreasing. So some amount of gain is decreasing here. So that variation or decrement is very, very less. So that's why even though there is a variation in the gain or reduction in the gain, we are preferring the negative feedback in order to improve the amplifier characteristics. Even though gain is reducing here, but the input impedance, output impedance, as well as gain parameters are enhancing here. So that's why we are preferring the negative feedback in the case of amplifiers. Okay, so while coming to the positive feedback. So when we add positive feedback to the amplifier circuit so that it will become the positive feedback amplifier, or else we can also call it as oscillator circuit. So the main advantage of the positive feedback here it is to generate the oscillations. When we provide the feedback for the amplifier circuit in positive way, it will generate the different kind of signals. So, but it is providing so many disadvantages. Though it is providing so many disadvantages, we can able to generate the different waveforms. So, because of that reason, we are preferring the positive feedback here. So, these particular signals, whatever we are generating from the oscillators, we can utilize in order to check any electrical or electronic devices, whether they are working properly or not. So while coming to the oscillator circuit, I have already mentioned oscillator is the positive feedback circuit. So this is the amplifier I am indicating with A, and this is feedback network. So this beta is the feedback ratio here. So this sample of this output signal we are taking here, that is the input for the feedback network, and the output for the feedback network is VF. So we are providing the positive feedback, so that's why we are indicating with the plus. So here in this case, Vn plus Vf we are applying for the input of the amplifier here. So the basic function of the oscillator is to generate the waveforms, that may be the sinusoidal waveform or non-sinusoidal waveform. So we can able to generate any kind of sinusoidal or cosinusoidal, triangular, pulse, square wave, etc. Different types of signals we can generate from the oscillator if we design different feedback networks and if we utilize different amplifier circuits. So generally in the case of amplifiers, we can use either bipolar junction transistor or field effect transistor or operational amplifier. So, but the basic oscillations are generated by the feedback network. So, according to our requirement, according to which waveform we required, we have to design this particular feedback network, and we have to design in such a way that it should provide the desired phase shift from this network. Okay. So, and the basic thing required for the oscillator is, in the case of oscillator, we are not providing any input signal. So that's why I mentioned Vn is equal to 0 here. So just we'll provide the supply, DC supply for the oscillator circuit so that we can able to generate the output signal directly. So that's why we can also call it as DC to AC converter, because we are providing only DC supply and we are getting the output as AC signal, that may be in any form, sinusoidal or non-sinusoidal form. So that's why oscillator circuit we can also call it as a regenerative circuit. The circuit itself, it is taking the input signal through the feedback and it will provide the output. And what is the basic principle required in order to operate the oscillator in proper way is, first thing, it should operate in the positive feedback. So that's why I'm calculating the gain of the positive feedback amplifier. So to calculate that, first of all, I'm taking the output voltage here. So generally, if you take only amplifier circuit, output voltage is gain into the applied input voltage. But in this case, we are adding the feedback also. That's why we need to consider the feedback voltage along with the input voltage. So that's why my input voltage is sum of the Vin plus Vf here. So that's why instead of Vin, I am taking Vin plus Vf here. actually in the normal case V0 into A Vn. This is for the amplifier only, and this is with the feedback. This is, if we apply the feedback, we will get this much. And if you multiply it with this particular gain, we will get it as AVin plus AVF. And what is our VF value here? So this VF value we will get from the feedback ratio. Feedback ratio is beta, that is equal to ratio of the input to this feedback network, that is V0, and the output to this feedback network, that is VF. So from this we can calculate VF equal to beta into V. So that's value and substituting here beta into V0. So if we take this V0 into the left side, we will get it as V0 minus A beta V0 is equal to AVM. So take V0 common here, 1 minus A beta equal to A into VM. So if we take V0 by Vn ratio from this equation, we will get it as A by 1 minus A beta. So here A beta is nothing but the open loop gain of the oscillator here. Okay, and here whenever our input voltage is equal to 0, at that time we need to get AB value as 1, so that we can able to get the sustained oscillations. So what is meant by this sustained oscillations here? Sustained oscillations means stable amplitude as well as stable frequency signal we will get from the oscillator circuit. That is nothing but without increment or decrement in the amplitude and without any variation in the frequency of the signal. How we can achieve that means when we maintain the open loop gain value as 1 and when we can maintain input signal as 0. And in order to design any oscillator circuit, we have one criteria, that is Barkasian criteria. So Barkasian is a scientist. He told two conditions in order to design any particular oscillator, that is AB is the open loop gain, just now we have calculated. So from that open loop gain we need to calculate the magnitude as well as the phase angle. So after calculating the magnitude of that open loop gain, that must be equal to 1, and also the phase angle provided from that loop gain is always 360 degrees or else 0 degrees. So in order to provide sustained oscillations, we have to achieve these two conditions here, magnitude as well as phase angle conditions included by the Barkasian scientist here. So this one we have already discussed, the gain of the oscillator circuit or pass-to feedback amplifier circuit. And I have mentioned in order to get the stable output without any distortion or without any clipping or increasing and decreasing of the amplitude, we have to maintain the magnitude value as 1 here. So that's why in this case we are getting the sinusoidal signal in the positive direction as well as in the negative direction with the equal amplitude. And if you see the frequency also, it is equally distributed between all the cycles. Suppose if I give my A beta value as greater than 1, in that case the amplitude of the signal will goes on increasing here. So these oscillators we can call it as overdamped oscillators, and this signal we can call it as overdamped signal. Overdamped means the amplitude is increasing here. And suppose if I am maintaining my A beta value as less than 1, in that case my amplitude of the signal will decrease here. So these particular oscillators we can call it as underdamped oscillators, and the signal generated from that oscillators we can call it as underdamped signals. So we doesn't require this overdamped as well as underdamped signals. Always we require this normal or without oscillations signals here. So these particular signal we can utilize in order to test any particular circuit here or any particular device here. And while coming to the RC oscillators. So these particular RC oscillators will provide the output signal with a frequency range of 20 Hz to 20 kHz. That is nothing but these are called as audio frequency oscillators. Why? Because those are generating the signals from 20 Hz to 20 kHz audio frequency range. Okay, so in order to design this RC oscillator circuit, we require one amplifier circuit as well as one feedback network. So here amplifier circuit you can utilize here it as BJT or FET or operational amplifier. So in this case, amplifier we need to design in such a way that it should provide the 180 degrees phase shift. So generally if you take BJT or FET, we will get common emitter configuration or common source configuration in the BJT as well as FET. We can able to achieve directly the 180 degrees phase shifted output across the amplifier. So that we can use either CE or CS configuration of the amplifier circuit here. So for this amplifier, we are providing the input as sinusoidal signal. So though it is the common emitter or common source amplifier, it is providing the 180 degrees phase shift. So that's why across the output of the amplifier, we are getting the 180 degrees phase shifted signal here. And the amplitude value is increasing here. If you observe in the input waveform as well as in the output waveform, the amplitude value is increasing. And at the same time, the phase shift 180 degrees is also introduced in the output signal. So this output signal, the same output signal, again we are applying to the feedback circuit. So in the case of RC oscillators, the feedback circuit we need to design in such a way that it should provide the total 180 degrees phase shift. So for this feedback circuit, we are providing this signal means the 180 degrees phase shift to this signal means again we will get the whatever the signal we are applying across the input. So if you compare these two signals, both are in phase. Okay, both are in phase signals. So that is the condition for positive feedback here. Always in the positive feedback, the input signal as well as the feedback signal should be in phase. In the case of negative feedback, always the input signal as well as feedback signal are 180 degrees out of phase. That is the basic difference between the positive feedback as well as negative feedback. And in the case of all the oscillators, we are going to utilize the positive feedback only, not negative feedback. So this is the actual structure required for the design of RC oscillator circuit. 180 degrees phase shifted amplifier as well as 180 degrees phase shifted feedback circuit. So in the case of RC oscillators, in the feedback circuit, we are going to using the elements resistor as well as capacitor only. So this resistor and capacitor combinations we are connecting different way. The combination of RC elements are the combination of only resistors or the combination of only capacitors we can utilize here. But the thing is we have to generate the 180 degrees phase shift in this oscillator. So these RC oscillators are divided into two types. That first one is RC phase shift oscillator and second one is Wein bridge oscillator. So while coming to the RC phase shift oscillator. See, in the case of block diagram of RC phase shift oscillator, we are using the inverting amplifier. So this inverting amplifier is providing the 180 degrees phase shift. Okay. So the output of this one we are taking here it as V out, and that one is equivalent we are taking here it as V1. So the input for this feedback network coming from the output of the amplifier. So here in the feedback network we are using 3 RC phase shift networks. So each RC phase shift network will provide the 60 degrees phase shift. So overall 3 RC networks, total phase shift is 60 degrees. So the overall phase shift provided from this feedback network is 180 degrees, and the phase shift provided from the amplifier is 180 degrees. So the overall feedback overall phase shift is 360 degrees, or we can also call it as 0 degrees. So that is the condition for positive feedback as well as for the oscillator. So this output again we are giving back to the input to the amplifier. So now we will see the internal circuit of this amplifier as well as this feedback network. So in the case of amplifier, I am taking the common emitter amplifier with voltage divider biasing here. So this is the common emitter amplifier with voltage divider biasing, and this CR and this capacitor and resistor and this capacitor and resistor, these three are the feedback networks. These three are the feedback networks. So in order to operate this particular amplifier, first thing we have to provide the proper biasing required for this amplifier. So that particular proper biasing is provided from this R1 and R2 resistances, or provide the required biasing for the transistor or the amplifier here. And this common C capacitor is nothing but the emitter capacitor. It is used to bypass any noise elements which are present across the output of the amplifier. And across the collector of the amplifier, we will take the output voltage. And one more thing, in order to operate it in the amplifier condition, we have to operate this transistor in the active region. So in order to operate in the active region, this base to emitter junction, we need to always forward bias, and this collector to base junction, always we need to reverse bias. Here it is forward biased, here it is reverse bias. And along with that, we need to provide the proper operating point in the active region, so that only it can able to provide the total amplified output without any distortion or without any clipping here. So the output of this amplifier, again we are applying to this cascading of these three feedback networks here. Okay, so the basic function of these three feedback networks are used to provide the total 180 degrees phase shift. And the output of this amplifier will also provide 180 degrees 180 degrees phase shifted and amplified signal. And this signal, the output of this amplifier, we are giving as the input for this feedback network. And the output of this feedback network, again, we are giving back to the input of the amplifier. Okay. So due to this feedback process, it will generate the sustained oscillations within the range from 20 Hz to 20 kHz. So in order to analyze this RC phase shift oscillator, I am taking the hybrid equivalent circuit of this bipolar junction transistor along with its related elements. So this one is the hybrid equivalent circuit of the bipolar junction transistor. So along with this, we are also having two resistors for the biasing. Those are R1 and R2 resistances. Okay, these R1 and R2 resistances I have included here, and this is the hybrid equivalent circuit of the BJT. So here 4 parameters we will be having: input impedance, reverse voltage gain, forward current gain, as well as output admittance here. So this is the exact model of the hybrid equivalent circuit of the bipolar junction transistor, and remaining elements, the feedback network, I have taken as it is here. This total part I have taken here it as it is. So only the transistor I replaced with the hybrid equivalent circuit. And in order to analyze this circuit, I wanted to simplify it as approximate model. So this one is available in the exact model with all the parameters. In the approximate model, we can able to neglect this HRE, V0 as well as this HFE, IB values. Why? Because these values are very less here. So that's why we can able to neglect that. In the approximate model, we already discussed why we are removing the two parameters here. So after removing this HRE, V0 as well as 1 by HOE here, not HFE. After removing HRE, V0 as well as 1 by HOE, we will get the equivalent circuit. It is nothing but in this particular circuit, we are neglecting this term as well as this term. So again, I am taking the total remaining circuit as it is here. HAE as it is and HFE, IB is as it is we are taking. The thing is, we have neglected HRE as well as 1 by HOE terms. Okay, and these resistors R1, R2 are in parallel combination. So that's why I replaced it with the parallel combination of single resistor. And in the circuit across the emitter, we are having the emitter resistance as well as emitter capacitance. So the same thing I have mentioned here, emitter resistor as well as emitter capacitance. And the feedback network. So this is the equivalent circuit using H parameter model of the amplifier. So for the analysis purpose, we are neglecting the capacitors. So that's why when we neglect the capacitors, so these RE also connected in parallel with that particular resistance. So it will also short circuited here. So the remaining elements are R1 parallel with R2 and HIE and HFE, IB and the feedback network. And if we compare this parallel combination of these two resistances and input impedance of the amplifier here. So generally the values of R1 and R2 are very large. But if you take the parallel combination of these two, R1 and R2, means the value will be less here compared to this HIE value. HIE value is more compared to parallel combination of R1 and R2 here. It is very high compared to this. So that's why we can neglect the parallel combination of these two resistances here. So that's why after neglecting this R1 parallel with R2 combination here, we will get this particular circuit. The remaining elements are as it is. The thing is, I removed the parallel combination of R1 and R2 here. So now, in order to find the frequency of oscillation, in order to generate the sustained oscillations, how much frequency we need to provide for this particular oscillator. In order to calculate that, I am taking only the feedback network. Why I am only taking the feedback network here means, depending upon the feedback network only, the phase shift is depending as well as required frequency of oscillation is providing here. So that's why I am considering only the feedback network. That is a combination of 3 RC networks. So here I am applying source transformation to this part. It is in current form now. Because HFE IB parallel with RC means it is in current source or in current form. So I wanted to convert it into voltage form to calculate the frequency of oscillation. So after applying the source transformation, so this will become HFE IB into RC. Why it is RC means opposite resistance we are having here it as RC. So that's why V equal to IR. So I value is HFE IB here and the value of resistance is RC here. So that's why HFE IB into RC. So once it is changing from current source to voltage source, so that's why this resistance is coming in parallel with this it is coming in series with this voltage source. So next I am indicating the currents which are flowing in the networks I1, I2 as well as I3. So next we need to find the values of these loops. That is nothing but different voltages. So to find that, first of all, I am applying the KVL to this first loop. This one I am taking it as my first loop. If we apply the KVL to this first loop, I will get it as minus HFE IBRC is equal to the drop across the collector resistance RC is I1 into RC, and the drop across the capacitor is 1 by j omega C1 into I1. And this resistance is in between first loop as well as in the second loop. So that's why R into I1 minus I2 here. So take I1 common here. So you will get it as I1 of RC plus 1 by j omega C plus R minus I2 R. So take it as the first equation. And similarly, take the second loop. I am considering the same circuit. In that I am taking the second loop and I am applying the KVL to the second loop. So if you apply the KVL to the second loop, in this particular capacitor, the drop is 1 by j omega C into I2. And this resistance, if we take this particular resistance, that is R into I2 minus I3 plus, and the drop across this particular resistance is I2 minus I1 equal to 0. So after simplification, we will get it as minus I1 R plus 2R plus 1 by j omega C into I2 minus I3 R equal to 0. Take it as the second equation. And similarly, apply the KVL for the third loop. So after applying the KVL into the third loop, we will get it as the drop across this capacitor is 1 by j omega C into I3 plus drop across this particular resistance is Ri3 and plus drop across this particular resistance is Ri3 minus I2 equal to 0. We don't have any voltage terms here. Minus Ri2 plus 2R plus 1 by j omega C into I3 equal to 0. This one take it as the third equation. So from these three equations, we can write it as the matrix form. That is nothing but these are the voltages coming from the three loops. From the first loop only we got minus HFE IBRC. From the second and third loops, the values of voltage is 0. And these are the values or coefficients we got from the equations, and I1, I2, I3 are the currents here. So I am considering this particular coefficient matrix here to find the frequency of oscillation. And we have to find the determinant of that coefficient matrix. So to find the determinant of that coefficient matrix, for simplicity, I am assuming the value of RC equal to KR and the value of j omega I am replacing it with S. So wherever the RC is there, I am replacing with KR, and wherever the j omega is there, I am replacing with S here. So after replacing that, we will get this particular matrix, determinant of coefficient matrix. So after finding the determinant of this particular matrix, we will get the frequency as 1 by 2 pi RC under root of 4k plus 6. And the open loop gain we will get from the oscillator is k HFE by 3k plus 1 minus phi alpha square minus k alpha square. That is equal to 1. So from this, we can get the value of alpha as under root of 4k plus 6. So HFE value we can write from this as 4k plus 23 plus 29 by k. So HFE, the simplified value of HFE is this much. So in order to get the sustained oscillations without any variations, we have to maintain the HFE value as this much. So to find the minimum value of HFE, we have to differentiate this HFE equation with respect to 0. So this is the HFE final equation. Apply the differentiation to this. After applying the differentiation of that one, we will get it as 2.69. The value of k is 2.69. So in the HFE equation, if you substitute the value of k equal to 2.69, we will get the minimum value of forward gain is 44.53. That is nothing but if the amplifier maintains the gain as 44.53 so that it can able to provide the proper amplified signal for the oscillation. So HFE minimum is 44.53 and the frequency of oscillation we got here it as 1 by 2 pi RC under root of 4k plus 6. So these two are the required things for the RC phase shift oscillator, designing of the RC phase shift oscillator. So what are the advantages of this RC phase shift oscillator? We can able to design in simplify this particular circuit. Why? Because here we require only the transistors, resistors and capacitors to design this circuit, and it produces the audio frequency range of signals from 20 Hz to 20 kHz, and it only provides the sinusoidal signals as the output. Why? Because these RC phase shift oscillators are the sinusoidal signal generators, and it produces the fixed frequency of oscillations, are that is nothing but it will generate the fixed frequency signals. So while coming to the disadvantages, here the frequency stability is poor. That is due to the changes in the components value or due to the temperature effect or due to the age factor. The frequency stability is varying here. And the frequency of oscillations can be always changed by changing the values of resistors as well as capacitors. So here we are fixing the one equation for frequency of oscillation, but if we change the value of RNC elements, the frequency of oscillation value will also vary here. Okay, so these RNC values of 3 sections must be changed at a time in order to satisfy the oscillating conditions. Then only it can able to generate the sustained oscillations. That is the drawback in the case of RC phase shift oscillator. And the next type of oscillator is the Wein bridge oscillator. It is also belongs to the RC phase shift oscillator. So to design this Wein bridge oscillator, we require amplifier as well as feedback network. So here in the case of amplifier, we are taking the two-stage amplifier. So why we are taking two-stage amplifier here means it should provide 360 degrees phase shift. So if you take single stage means that will provide the 180 degrees phase shift. So we are taking 2 stages. So that's why 180 degrees plus 180 degrees to overall it will provide the 360 degrees phase shift that is required for the oscillator. And the feedback network we are designing in such a way that it should provide 0 degrees phase shift. That is nothing but what is the phase shift required for the oscillator we are generating from the amplifier itself. So that's why no need to get any phase shift from the feedback network. So that's why 0 phase shift it should provide. Okay. So the input for this two-stage amplifier we are giving here it as Wein. So the output of this two-stage amplifier is the amplified version of the input signal without any phase shift. 360 degrees means almost it is equivalent to the 0 degrees only. So that same signal we are applying for the feedback network, and the output of feedback network we are taking here it as V2, and again we are giving back to the input to generate the oscillators here. So this is the internal circuit of the Wein bridge oscillator. So this part is the amplifier, two-stage amplifier circuit, and this is the bridge or feedback network. Okay. So here for these amplifiers we are providing the biasing required to operate these amplifiers. So the output of first stage amplifier through the capacitor we are connecting to the base of the second transistor here, and the output of this amplifier, that is the last stage or second stage, we are connecting back to the input of the bridge here. So here this one is the negative feedback. This R4 resistance from the bridge will provide the negative feedback, and this will provide the positive feedback. That is nothing but in the case of Wein bridge oscillator, we are utilizing both the positive feedback as well as negative feedback in order to achieve more quality of the signal. So in the case of feedback network, so about these amplifiers, we know we are taking even single stage or multi-stage amplifiers, we are getting the amplified version of the output across the amplifier here. So that output again we are giving back to the feedback network here. Okay, this is the feedback network. Okay, and in this Wein bridge we are taking 4 resistors R1, R2, R3 and R4 and 2 capacitors C1 and C2 here. So this combination of R1, C1 and R2, C2 are acts like a lead and lag networks. So here the lag networks are used to increasing the frequency, and lead networks are used to increase the frequency of oscillation, and lag networks are used to decrease the frequency of the oscillations here. See here from the circuit we can say R1 resistance is in series with the capacitor C1, and this R2, R3 as well as R4 are in parallel with the capacitor C4 here. Okay, so capacitor C4 are these 4 are the 4 arms of the bridge here, and these 2 transistors are used to generate the 360 phase shift as well as to provide the positive feedback. So that's why here I have mentioned here it has positive feedback from the amplifier, and here it is the negative feedback from the feedback network. So the negative feedback is connected to the circuit output with the range of frequencies here. At what frequency range we require that feedback we need to provide here. And through R4 resistance we are providing the feedback. It will increase the current of the circuit here. Okay, so here if the amplitude increased, then the more current is offered, so we will get the more negative feedback for the circuit. Okay, so here this amplifier will provide the total 360 degrees. I have already mentioned 180 degrees with the Q1 transistor and 180 degrees with the Q2 transistor, and the output of this Q2 we are giving back to the bridge circuit as the positive feedback. So here R4 provides the degenerative effect, that is nothing but negative feedback. Degenerative effect means negative feedback, and R2 provides the positive feedback, that is regenerative feedback, that is positive feedback. Degenerative means negative feedback here, and regenerative means positive feedback. Okay, and this C1, C2 variations will decide the changing frequency of the circuit, and also R1, R2 variations will decide the range of change, how much change we are getting in the frequency of oscillations is decided by the R1, R2 components here. So this circuit I can replace with this bridge I am keeping as it is. The amplifier circuit I replaced with the single block here in order to find the frequency of oscillations. See here, the output of the amplifier we are applying between the 1 as well as 3 terminals here. Okay, output we are connecting here, and the 3 terminal we are grounding here, which is the input to the feedback network here. So the output of this feedback network between 2 and 4 terminals as applied to the input of the amplifier again. Why? Because the output of the feedback network acts like input for the amplifier again here. So here Wein bridge oscillator is utilizing the non-inverting amplifier so that it will provide the 0 degrees phase shift. So the 2 arms of the bridge, those are R1, C1 are in series with the and this R2, C2 are in parallel. So these 2 arms of the bridge are used to provide the frequency of oscillations. So again I am considering only this feedback network. From this feedback network only we can able to find the frequency of the oscillations. So the 4 arms of the bridge I am representing in this way here. So between 1 and 4, we are having the R1 and C1 series resistances, and between 3 and 4, we are having the R2, C2 parallel combination. So these two and these two I am taking here. Okay. So these R1, C1 I am taking here it as the impedance Z1, and this parallel combination of R2, C2 also I am taking here it as the impedance Z2. So the output of amplifier V0 is applied as input to the feedback between 1 and 3 I have mentioned, and the output of the feedback network again we are connecting between the 4 and 1. So I replaced these combinations with Z1 and Z2 in this circuit. So Z1 value is series of R1 and C1, and Z2 is the parallel of R2 and C2. So if we substitute the values of this R1, Xc1 is the 1 by j omega C1. So the value of this one is 1 plus j omega R1 C1 by j omega C1. And the parallel combination of these two is R2 into Xc2 by R2 plus Xc2. So substituting the values of Xc2 as well as R2, Xc2 is equal to 1 by j omega C2. After simplification, we will get it as R2 by 1 plus j omega R2 C2. So Z1 value is this much and Z2 value is this much. So these two values we are going to utilize for finding the oscillations, and before that we require the current, how much we are getting from the circuit. That is, to calculate that current in the feedback network, we are taking this voltage V0 divided by these two impedances Z1 plus Z2. And to find the feedback voltage VF is drop across this Z2, that is I into Z2. And the value of I is V0 by Z1 plus Z2 into Z2. So beta is the feedback ratio we are getting from the feedback network, that is feedback voltage by output voltage. So from this we can get feedback voltage by output voltage. The value is Z2 by Z1 plus Z2. So we got all impedances Z1 and Z2, and the current as well as feedback voltage as well as feedback ratio. So I am taking all that parameters here, Z1, Z2 as well as beta. Beta is the feedback ratio. Just now we have calculated. So in the beta, we are having Z2 by Z1 plus Z2. So substitute all the values here. This is the Z2 value into 1 by, this is Z1 plus Z2. Okay. And after simplification, we will get this particular equation. And for further simplification and also to find the frequency of oscillation and to find the gain, we are multiplying and divide with this denominator, 1 minus of this denominator, multiplying and divided with the 1 minus of this denominator. So in that, after multiplication, we will get the simplified expression, this one. After multiplying these terms with this numerator to numerator and denominator to denominator, we will get it as this much. So to find the frequency of oscillations, I am taking the imaginary part of this beta here. In the imaginary part, we are having j omega C1 R2 minus j omega cube R1 R2 square C1 square into C2. So in that, I am taking omega C1 R2 common. If we take that, we will get it as this much. I am equating it to 0 to find the frequency of oscillation. So this one, if we take right side, it is also 0. And this omega C1 R2 will also, if you take right side, we will get it as 0. So the value is 1 by omega square R1 R2 C1 C2 is equal to 0. So from this, if we find the omega value, we will get it as 1 by root of R1 R2 C1 C2. And here omega is equal to 2 pi f. So from this, if you write the frequency f value, we will get it as 1 by 2 pi under root of R1 R2 C1 C2. Suppose if you take, to design the bridge, if you are taking both the R1 R2 are same, as well as C1, C2 are same, we can replace it with the R and C, so that the frequency of oscillations is 1 by 2 pi RC, or else omega equal to 1 by RC. So this is the required frequency to generate the proper oscillations. So this is for getting the frequency of oscillation. And next, how much gain we need to provide. For that, we have to take the real part of the beta, that is feedback ratio. Beta value we have calculated already here. So to find the frequency of oscillation, we have considered the imaginary part. To find the gain value, we are going to take the real part of this equation. So after taking the real part of this equation, we will get this much. And after simplifying this equation and after applying again the same resistance and capacitance conditions, we will get beta value as 1 by 3. So according to Barkasian criteria, the magnitude of the loop gain should be greater than or equal to 1. So if we apply that particular condition, we will get the loop gain value as greater than or equal to 3. It is satisfying the condition of Barkasian criteria. Actually, it should be A beta value is greater than or equal to 1. So it is, we are getting here it as 3. So in order to design any Wein bridge oscillator, the frequency of oscillation should be 1 by 2 pi RC and the gain should be greater than or equal to 3. So that we can able to generate the sustained oscillations. So while coming to the advantages of this Wein bridge oscillator, it uses both the positive as well as negative feedback so that it can able to provide the better gain as well as better stability of the signal. And overall gain is high because of cascading of 2 stages of amplifiers here. So the frequency of oscillations we can easily vary by varying the values of resistances as well as capacitances in the bridge network. While coming to the disadvantages, frequency is not more stable when we change the values of elements, that is resistors and capacitors. If we fix it with one particular value only, it will provide the sustained oscillations. And it cannot be used to generate the high frequency of oscillations. It is applicable for only audio frequency range, that is from 20 Hz to 20 kHz range. And this particular Wein bridge oscillator we can utilize for audio testing and in order to generate the clock signals for testing the filter circuits and in order to testing the distortion levels in the power amplifiers. So in this session we discussed about construction, operation and analysis of RC phase shift oscillator as well as Wein bridge oscillator. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.